Okay, morning. Okay, so we'll keep continuing on the discrete state model here. Okay, so in the previous lecture, we looked at how to obtain discrete state space model from a pulse transfer function. So now we're going to look at another way, basically another branch of getting this discrete state model, and that is basically from a continuous state space model to discrete state space model. Okay. So basically, the idea is just discretize continuous state space model. Okay. And where does continuous state model from? You know, it's from your Laplace transfer function or from differential equation, right? Yeah. So let me write down the continuous state space model in generic term. It will be x vector, okay, it's continuous derivative, equal to a system matrix times the state variable vector, okay, times u times t. Okay, so that's a continuous state space model, and what the idea is, the objective is to go from here and trying to obtain x of k plus 1, okay, equal a x of k plus b u of k, and then y of k, okay, as we're going to see that, okay, it's actually c is not going to change, okay, and d is not going to change. Okay. So basically, to get this from continuous to discrete is basically find a and b in terms of this f and g at here. All right, yeah. And that's the process we call it. It's a discretization process. Yeah. More specifically, we're actually going to consider the process here is considered the zero order Hopf equivalent. Okay. So in other words, we're considering basically your continuous system here is preceded with a zero order Hopf, okay, and that's the discretization process. Yeah. Okay, so let's take a look at how do we get from here to here, right? Yeah, but first of all, okay, let's focus on the continuous system here, and we'll focus on this state equation, okay, the state equation here. So let me rewrite the state equation. And actually this time I'm going to rewrite it like this. I'm going to move all the x term to one side. Okay, yeah. So basically move that to the other side. So as you actually learned in previous lectures, particularly problem 246, first order system, first order differential equation. Let's see if I have first order differential equation, y dot plus px times y and equal to q of x. That's first order differential equation, and it's non-homogeneous, right? Okay, so I want you to compare these two at here, even though this is a vector format and even though this is a matrix, right? But in general format, this is also first order, right? First order format here. So when I try to solve for this first order differential equation, if you remember from previous lecture, there is this approach called what? Integrating factor methods, right? So what do you do with integrating factor? Basically, you multiply each side of the equation with a so-called integrating factor. That's what we call the sigma. Okay, we call it sigma here. Then the sigma, what we try to do is we're going to try to basically find the proper sigma such that the left side can be rewritten into this product rule, right? So basically sigma y sigma y prime or derivative, if you expand it using product rule, you get exactly the same thing here. Okay, yeah, and that's basically the way to find the sigma. And in order to satisfy this condition, basically in order to satisfy this condition in here, we can easily find the sigma prime equal to sigma px. So in order to satisfy this, we need this condition here, sigma prime equal to sigma px. And this is a simple first order differential equation again, and you can use separating variables to solve for sigma. So sigma prime basically is d sigma over dx equal to sigma and x p of x. So separating variable, move the dx to this side, move the sigma x to this side here, so you can basically integrate both sides and solve for sigma, right? Yeah. So anyhow, you know, your sigma can be solved, which is equal to, okay, so this is basically the integrating factor, right? The integrating factor for a first order differential equation. Is that good? Yeah. Okay, so then let's come back over here now, okay? I said I'm trying to solve this guy here, right? Try to solve this. And well, we can try a similar approach, integrating factor. Now if I do a comparison at here, this p of x here is what? This p of x here is the coefficient for the y, right? So for this particular one here, the coefficient for x is, for x vector, of course, is which one? Is f or minus f, right? So it's this guy here, okay? So if I want to try this integrating factor methods, basically what I'm trying to say is I'm trying to find the integrating factor for this differential equation, right? For this differential equation. So then for this differential equation, what is sigma now? It's not going to be a scalar, but if I just use this notation at here, it's actually what? E to the power of integral. This p of x is negative f, right? And x in this case is t, so dt, right? Yeah. And the other thing is f here is a matrix. We're talking about a linear time invariant system, so the f matrix is actually not a time variant matrix, right? Or in other words, it's just considered as a constant. Okay, so if it's constant, the integral of this constant basically is just ft, right? That makes sense? Yeah. Okay, so basically this is my integrating factor at here for this differential equation. And of course, you got to basically, we'll go back to the reality here. The reality is, I mean, f is a matrix, right? F is a matrix, and this is basically an exponential, right? This is an exponential of a square matrix. F is square, right? Yeah. So as we're going to see later, if you get rid of that negative sign, you actually learned in your modern control system, when you get rid of the negative sign, F is a continuous system matrix. What do you call that again? It's called state transition matrix, right? Ring a bell? No? Really? Okay, so anyway, now I'm going to multiply this matrix back into this differential equation at here, okay? Yeah. So that's my So this is what happens is I'm multiplying this integrating factor at here back into this differential equation. Okay, so I know this is my integrating factor. So why is it called? Because why? Because then I can rewrite the whole left side into what? Into this format here, right? Into the format. So basically, this is my whole left side here. Then I can write it into what? Into a derivative. This is derivative, right? And this is the variable is t, independent. So d over dt. E to the power negative f of t. That's sigma. The y here is x of t. Okay? Yeah. Was that good? Yeah. And the other side, we'll just keep it as it is. Okay. All right. We're almost there. So, because idea is to solve for this differential equation. In other words, trying to solve for this x of t, right? Solve for the x of t. So you can multiply this dt to this side here. Okay, so multiply the dt to this side, and basically you end up with a d bracket dt. So now what can you do? Integrate both sides, right? Integrate. Okay, yeah. So let's say we're integrating from t naught to t, basically from initial time to a general time. Okay, so t naught could be 0. Okay. So if we do this, and what does the left side give us? I mean, this is just a d bracket here, right? So the integral of the left side is actually just whatever this is. This is the antiderivative, okay? And then you sub the limit into this antiderivative here. So what do we get? We get e to the power of a negative ft x over t, right? And then minus e to the power of f of t t naught x t naught. Okay? Yeah. Is that good? Yeah. So the other side, I don't know what it is, so we'll just leave the other side as it is, okay? But I can actually move this minus sign to the right side, so I'll just save myself one step here. So okay, so there, right? This is basically the solution. You see here, right? So this is a x over t, the solution, right? It's coming out. Okay, it's not quite clean yet because there is a e to the power of negative ft at here. So to clean it up, let's multiply, right, both sides by e to the power of a positive ft. Okay. Yeah. So apparently this multiply this is just 1, right? And this is just x over t. And now multiply by this. So this is e to the power of a times e to the power of b, which is e to the a plus b. So this is e to the power of what? F. Okay. Yeah. And x of t naught. And then this side here, this is e to the power of ft. Okay. So I think I need to be a little bit clear here now. Because why? Because see, I have a integration up to t, isn't it, right? And the integral inside here, dummy variable is t, right? So generally, in order to have a less confusion, instead of using t at here, so let's choose a different dummy variable. Maybe we can choose a tau. Is that good? Yeah. So basically, here, here, here. So we should probably choose a different domain variable here. Okay, let's choose tau. Okay, so we're not changing anything. Okay, yeah, but it does make it actually clear, because see, I have a e to the power f of t here, right? And that's not part of this integral. Okay, that's not part of this integral here. So which means actually I can what? I can move this one into this integral here. So basically, I can move this into here, so that'll give us e to the power of capital F t minus tau, isn't it? Okay. There. That's the solution. Okay. So this is basically the solution for the continuous state space model. Okay. So you have an initial condition for the state variables, then you plug it here. Okay. You're supposed to get a response like this based on this solution here. Okay, yeah. So in particular, this e to the power f of t. Okay, if you remember that I said it's the exponential of a square matrix f right here, right? Yeah. It's defined as this: a identity matrix. So it depends on the size of the matrix f. If matrix f is 3 by 3, then this is a identity matrix 3 by 3. Okay. Plus ft plus 1 over 2 factorial. So if you see this, does that ring a bell? Yeah. You see that you should see that in the modern control system here, right? This guy here. Is that good? Right? Yeah. And there are actually a couple of properties, associated with this one. This is what I said. This is called state transition matrix. Okay. Yeah, more precisely, probably it's e to the power of f of t minus t naught, but okay. Okay, so and there's some of the property, like one of the property is if you take derivative of this, okay, and you get this. Okay, so it's basically very similar to take it as a constant, though, huh? Yeah. Later, when we look at focus on discrete time system, discrete states model, we'll look at what is the state transition matrix for discrete state space model. Okay, yeah. So state transition essentially means, this matrix times the initial condition here. If your initial input is 0, then your output is basically just all based on initial response, right? Yeah. So that matrix right here essentially brings the initial response to wherever the final state is. Okay, that's called the state transition matrix. And what are we trying to do then? Go back to the initial. We're trying to discretize this in continuous model. Basically, discretize this guy with a zero-order Hall equivalent, okay, approach. So here's your continuous response. Then how can we discretize this guy here, basically, right? To make it a zero-order Hall equivalent. Okay. So here comes basically the core part here. Zero-order Hall equivalent, okay, of this x of t dot equal to f x of t plus g u of t. Okay, yeah. So here's what we're gonna do. Okay, we're sampling. Basically, we started to do this kind of a structure now, right? So we're gonna have a sampling time. Okay. So sampling time basically means we are sampling from tk moment to tk plus 1 moment, for example, right? And the difference between these two okay, is the sampling time. Okay, yeah. So if I'm gonna do this, I'm gonna go back to this solution in here. Okay, go back to the solution. So the question, let's say if I ask you a question, forget about tk or tk moment. You know, the question here is, if this is a t naught, the initial time moment, right? Okay, and then ask question is, okay, what will be the system response? What will be the value of system response? You know, from t naught to t naught plus capital T to the next time instant. Does that make sense, right? So if you are asked this, what do? You basically just change this the small t at here to a specific time instant, right? Yeah. So in other words, I'm gonna do this. I'll consider the tk moment as the initial moment, and then I consider tk plus 1 moment is the time instant I'm trying to compute, right? Trying to calculate. Okay. So what do? We're gonna replace the t naught with tk, and replace the t with tk plus 1. Okay. Yeah. So then let's see what do we have now. So just basically do all the replacement except the tau, except the tau here. Okay. Yeah. Okay. So now what I'm saying is we're trying to t naught to tk and tk plus 1. Sorry, t to tk plus 1. Okay. Yeah. Then my solution. No, this is what? Tk plus 1, right? Tk plus 1. Okay. And does that equal to e to the power of f? Okay. Look at this one here. E to the power of f, tk plus 1 minus tk. Now what is the tk plus 1 minus tk? Yeah. Sorry. Tk plus 1 minus tk equal to capital T, right? Yeah. So we can replace that easily here. Let's wait here. So this integral limit becomes tk to tk plus 1. And e to the power of f, tk plus 1 minus tau, okay, and g u of tau d tau. Okay, that's the solution, right? That's the solution. Okay.
We ever need to know how to drive that?
Probably not. Yeah, but I guess I had to teach you this, right?
Yeah. No,
yeah. So, yeah, truthfully, you know, all 4 years, you probably don't remember a fraction of all the derivations that you have learned, right? But you should roughly know where it's from, right? That differentiates. Yeah. Okay, so let's go from here. This guy equal to capital T, right? Okay. And this guy here, I'm not going to change that. So let's just let it stay as it is. Okay. Okay. Now let's consider the keywords zero order hold equivalent. Okay, zero order hold equivalent. So what does zero order hold equivalent mean, right? Zero order hold equivalent basically means what? Here is, let's say this is a tk moment, and this is a tk plus 1 moment. Okay? Yeah. So during this interval, zero order hold, the control input to the system, right? The control input to the system, does that change? No, it doesn't, right? Which one is my control input? See this guy here, right? This guy. It doesn't change. It actually maintains at what value? So during this tk to tk plus 1 moment, the control input maintain at the level of u of tk. Exactly, right? So this is u of tk. Basically, it maintains the level here. So because this is a zero-order whole equivalent, so within this integral here, the u of tau, actually you can replace that with u of tk. Okay? Yeah. So. Oh, sorry, did I miss the one term here, right? X of what tk, isn't it, right? Okay. And plus this integral here, so I can replace this as a u of tk, and the G is this matrix, and G is also time constant basically matrix. So in other words, I can take the G out of this integral at here, right? Yeah, it's constant. And then this is basically u of tk is also constant now, right, with respect to this integral. So then this integral altogether becomes times g times u of k. Okay? Yeah. Is that good? Yeah. So the solution is based on this replacement. You get this expression in here. Now the idea is discretizing, right? Discretizing. I mean tk plus 1 moment. Really, it's what? Tk plus 1 moment in terms of our sampling. You know, when you say, oh, tk plus 1 moment, it's really just k plus 1 times t, isn't it? Right? Yeah. And tk moment, it's really just k times t, right? K times t moment. Okay? Yeah. So in other words, I can actually rewrite this solution at here now. But before we do that, let's do a little bit definition here. I'm gonna let a equal to this. Okay, a equal to e to the power f of t, and then b. Okay, this b is everything in front of this u of k. Okay. Okay. Yeah. And then I'm going to replace this tk plus 1. I'm going to replace, sure, yeah, we can do that. I'm going to replace the tk plus 1 with k plus 1 times capital T, and tk with kt. Okay? Yeah. So then what do we end up with now? X of k plus 1 capital T equal, this is a here, right? A times x of kt plus b times u of k. Look at that. That's exactly the kind of format we're looking for, isn't it? Right? Yeah. So basically, the A and the B, they are two matrices. They are the discrete, the system matrix for the discrete state space model. Okay? Yeah. Is that good? Yeah. Okay. So the only thing is the A seems good. You know, well, that's pretty, clean. E to the power of capital F T, right? The B at here is a bit of messy, right? So let's clean up the B a little bit here. Okay? Yeah. For the B, so for the B at here, so what we're gonna do is we're gonna do this. We're gonna basically do a little bit the so-called the change of variables, right? Let's do a little change of variables. So what is change of basically integral? So you don't want to change. You don't want to integrate with back to the tau anymore, right? So what you can do is let lambda equal to this. Okay. Let lambda equal to this guy here. Okay. Then what is d lambda? Right? Yeah. And we're basically trying to integrate with respect to lambda now, right? Into lambda. If we're going to integrate with respect to lambda, then the integral limits, which is for the tau, should also change, right? So how do we change the limits? Based on your substitution here, right? You change variables, okay? Yeah. So I'm going to skip that step here. Basically, when you sub the tk over here, that's the lambda minimum limits, right? You place that here, that's the maximum limit, okay? Yeah. Or maybe let's do that. Okay. So what does the b become now? If I do this, change variables, the lower limit for the integral tk, you plus the tk over here becomes capital T, right? The upper limit you put it here becomes 0. Okay? And this e to the power of f times the whole chunk is e to the power of f lambda, right? Okay? And d tau, what's d tau? It's a negative d lambda. Okay, and then times the g, right? That's the g. So this is a negative. This is t to 0. So as you learned, if you change this to 0 to t, you have a negative, right? And then negative and negative cancel each other here. So basically, okay, I'll put a g back into here, okay? So on the same thing. Is that good? Now this is the b now, right? This b looks much better than the previous one. Okay, yeah. I would rather deal with this one, okay? Because you really have this sampling time shows up here. So in other words, a equal to this and b equal to this. How do we, back to the original one, how do we get the discrete how do we get the discrete state space model, right? We need to obtain the a and the b, and a and the b expression are, this is one here, and this is one here. Okay? Yeah, there's two. That's it. Okay. Okay, so now let's basically next we'll look at is down to the earth. So I'll show you an example shortly. Okay, it basically is this integral. You can't do that. Actually, you're really tempted to do it, to integrate this integral like a regular integral, right? Yeah. The reason is, you can try, you see here, this f here, right? If you treat this as just a single constant, I mean, what is the integral of e to the power of at dt, which is what? 1 over a at, and then limits, right? So, if this f here, if I put the f, substitute to the a here, 1 over f, well, maybe that's what f inverse, right? Because f is a matrix, okay? But the thing is, as you're going to see later, system matrix, f is a system matrix, right? F is a continuous time system matrix here. The f not necessarily is always a non-singular matrix. Yeah. So if it's singular, then you can't take the inverse, right? Yeah. Very good. Okay. So you'll keep this one as it is, okay, and you will still be able to get an answer here, okay? Yeah. Okay. So now the question here is, right? How to get this first word e to the power of ft. Okay, that's basically our a, right? That's the a matrix. And then the next is how to get this b here. Okay. As a matter of fact, as you can see, the key is actually to get this e to the power ft. You see that, right? If you suppose you get e to the power ft now, remember what is e of ft is? E of ft technically is this, right? Is this. And if you expand everything out, you know, this is going to give you a matrix essentially. Okay, and let's give you a square matrix. Give you a square matrix size as f here. Okay, yeah. So maybe I should say this, not the EFT is E of capital T, right? EA is E of capital T here, huh? Yeah. So basically, as you can see, maybe what we can do is we get e to the power of f small t first. If I get this, then I can do what? I can let that small t equal to the capital T, right? Then I get this A matrix, right? And also for the B matrix here, if I have this guy here, and I can replace the small t with the lambda, and then this is going to be a matrix, huh? This matrix times another one, and then I will do the integral. Basically, the integral is with respect to each one of the elements. Okay, each one of the elements, and that will bring me the B matrix ultimately. Okay, so the key part here now is, you know, basically try to get this e to the power of ft. And where is e to the power of ft? E to the power of ft, if you look at this original system here, e to the power of ft is over here, right? See that, right? It's showing up. Remember what I said, I call the state transition matrix as continuous state model, right? Yeah. So here's what happens here. So I'm going to say is let t naught equal to 0. Okay. Remember in the solution for the continuous system, there's a t naught, right? So I'm going to let the t naught equal to 0. If t naught equal to 0, what is the solution now? The x of t equal to right? That's the solution, huh? Yeah. Okay. Yeah. Okay, so doesn't look like I can do anything at here, right? Because you probably would argue, okay, can I calculate this e to the power of t using this expansion here? This expansion is actually just like a Taylor series expansion. Okay. Of course you can. You actually, you know, basically depends on how many terms you take, right? Yeah. Actually, sometimes if you take 4 or 5 terms, it's probably already converged. Okay. Yeah. Not much change anymore. But you can see how difficult is it, right? You're gonna have to calculate so many calculations here. So let's look at the other way around here. I'll bring that continuous system model back into the picture. Okay, yeah, so this is a continuous state equation, right? This is a differential equation. Okay, and then I'm going to take the Laplace transform. We'll take the Laplace transform of both sides of this equation. Okay, take a Laplace transform. And Laplace transform for x of t is capital X of s. Laplace transform for the derivative x of t is what? Is s capital X of s, and then you have to consider the differential, the initial condition, and that's basically minus x of 0. Okay. Yeah. Does that ring a bell for Laplace transform? It's very similar to the z, right? When you take the z transform of x of k plus 1, what is the transform? Z times capital X of z and then minus an initial condition, right? Yeah. Okay, so the other side is capital F x of s plus g and u of s. Okay, yeah. Okay, so move this x naught. Okay, move the x naught to the other side, and move this capital F of s to this side here, because these two are common, right? These two are common. Okay. Then take out the common factor. Okay. So I added a identity matrix set here. So because this is not a constant everything, right? It's not a single variable. This is a vectors. So s times this vector. So when you take out the common factor out, right? You should have this identity matrix set here. Okay, and then minus that. Okay. Now you must have seen this, right? In water control. Okay. Yeah. So then I'm going to take the inverse of this guy. So that means I get what? Okay. Yeah.
Explain why you stuck the identity matrix in there again? Is that because F's a matrix?
Come again?
Can you explain why you put the I there, the identity matrix?
This matrix? It's more of like this, right? You can use an example here. Let's say S times a vector 1, 2, 3, right? And here is a matrix. You minus a matrix. This is maybe I use it. Let's say use a just 2 by 1, for example. Okay, so 1, 2, 3, 4 times the vector 1, 2. Is that good, right? Yeah. So when you're taking this out as a fact, if you don't take this common factor, then s times this, right? And this times this times this. So that's two vectors subtracting each other, isn't it, right? But if you take this out as a common factor, okay, and then you see you can use just a single scalar times minus a matrix, right? Yeah. So this is why we put I here. And as you can see, you put an identity matrix. There's no change, right? Same results as you do this separately, basically. Okay. Yeah. Okay. So now I can stop it here. Remember the idea. What's the idea here again? The idea is to get e to the power of ft, right? Now let's compare these two. Okay, compare these two expressions here. What's this guy? This is in terms of time, right? It's continuous time domain. Okay, and this is in the s domain, isn't it, right? But you can always basically change this s domain back into the time domain, right? By doing an inverse Laplace transform. But if you do that, if I compare, this is an initial condition, this is initial condition. So if I take this inverse Laplace transform, then in other words, the inverse Laplace transform, this coefficient here, should be the same as this one, right? Should be the same as this. Okay? Yeah. So that gave us the conclusion. So e to the power of ft equal inverse Laplace si minus f inverse, okay, of this. Okay, that's e to the power of ft. Okay. In the next lecture, when we learn similarity transformation, I'll show you another way of computing this e to the power of ft. Okay? Yeah. Basically, we can diagonalize a system matrix, okay, using the similarity transform. Okay. and then e to the power of the system matrix, okay, given a diagonal matrix is much simpler. Okay. So you might think, you know, is that really making our life easier, right? Actually, it is. Okay. Instead of, so if you compare this with this guy here, okay, you still have a much less computation. Okay. Yeah. Okay. In MATLAB, you don't need to do this. In MATLAB, there's a command called expm command. Okay. Yeah. So all you need to do is basically you can use a symbolic here, say sims t. Then you can call if you call this is a phi, then phi equal to expm. Define that at capital F first times the small t. Okay, and then it'll give you the result. Okay? Yeah, it may not be very accurate sometimes numerically. Okay, yeah. But that's a shortcut for verification. Okay. Okay, so let's move on from here. Okay. Before we look at a specific example here, okay, let's look at one more short item in here. Okay, then we'll look at the example how to get from a continuous states model to a discrete states model. Okay. Yeah, but the thing I wanted to talk about right now is basically how do we get the pulse transfer function, PTF, the pulse transfer function from a discrete state space model. Okay, yeah. So you see, you know, you basically you got to be clear is here is my plant. Okay, here's a plant. We're discretizing the plant, and we're discretizing it with a zero order Hall equivalent. Okay, yeah. So if you think about all the different ways of doing this, remember, if I do this, I can get what, a g of z like this, right? And then I can from g of z to a discrete state model, state space. Okay, yeah. Or from here, from this g of s, we get a continuous state space model, right? And then you from the continuous space model, you get from this discrete state model, right? From the discrete model, you can get back to this pulse transfer function here, right? So they're all intertwined here, but they all talk about the same thing, though, right? Yeah. So nothing should change, though. So here is our state space model. Suppose we had it already. Okay. Yeah. So how do we get the pulse transfer function? Basically from here back over here. Okay. And from here to here, we're using zero order Hall. This is what we just talked about today, right? So how do we get back here? So what we do is this. We take the z transform, z transform of both sides of this state equation here. Okay. So if you take the z transform of both sides here, okay. So what do we get? On the left side here, we get z capital X of z, right? Okay. And minus the initial condition, okay, and plus and equal to the other side, a capital X of z plus b and u of z. All right, yeah. And the last equation here is y of z equal to c x of z plus d and u of z. Okay, we're deriving the pulse transfer function, which means what are we deriving? We're deriving what? The ratio between the output and the input. The input is u of z. U of z, yeah, right? Yeah, that's what we're deriving. Okay, yeah. Okay, so from the first equation here, from this one here, basically you move this ax of z to the other side. Okay, very similar like Laplace style, right? Take out the common factor. Okay, then you have a zi minus a now, right? And then you do the inverse. Okay, so you will get capital X of z equal to this. Okay, with initial condition 0. Okay, with initial condition 0. Because when you're deriving the transfer function, just like the continuous system, transfer function, the condition is you consider initial condition as 0. Okay. Yeah. Okay. So this is a capital X of z equal to this. Then we substitute into this expression for y of z. So c times this whole bunch. Okay. Is that good? Yeah. It's a lot of writing there.
So it's supposed to be u of z.
This here?
Up 2 marks.
Oh yes, you're right. Good. Okay, so now I have a common factor u of z here, so which basically give us a pulse transfer function, the ratio, which is c times zi minus a inverse times b plus d. Okay. Well, that's basically something you will have to remember, right? If you don't want to know where it is from. The capital D term. Capital D term is it's most of the time is 0. You know, there's nothing there, so it's what you're dealing with is this part here. Okay, dealing with this part. All right. So, any question? Yeah. Okay.
Just had one, scroll up a little bit.
Yeah.
Your notation, your continuous S, so down a little bit. Where you draw the
Here?
the whole 0. Yeah.
Yeah.
Continuous, is that state space or
State space.
not space?
No, state space. SS state space. Yeah. And this is only for G of S. Okay. Yeah. Not including this. Yeah. Okay, so let's take an example here. I'm giving you a continuous system model. Okay. So this is the kind of a model very similar to the experiment that you're gonna do or do your project, the experiment setup. Okay, so it's basically generally you can consider it as a control input and precision output, okay, of the system. Okay, yeah. Okay, so what we're trying to do is we're trying to obtain the discrete state space model based on this guy here with a sampling time, let's say equal to 1. Okay, yeah, that's what we're trying to do. So now think about this. This is basically the sort of a diagram, right? You look at where are we starting with, right? We're starting from which location? Here, right? Here. We're trying to from here to here, right? Yeah. And we're not going through this route here. We're not going to go through this route. We're going to go through this way here. Okay? Yeah. So in other words, we're going to have to obtain the continuous state space model first, and then use what we learned today to discretize it, right? Okay. Yeah. So what is the continuous state space model for this guy? And that's a different story, basically, as to obtain the continuous state space model. Now, here's what I generally would recommend you to do here. Here's y of s, u of s, like this, right? Yeah. Let's put this one back into the differential equation. Okay, back in the differential equation. Then, what does that mean? Basically, y of s times this whole chunk equal to u of s, right? Okay, and the bottom here is s squared plus 2s. S squared, s, just s itself, always represent is not an integrator. S, a derivative, right? So s squared must be a double derivative. So s squared times y of s, when you convert it back into the time domain, you actually get what? Y double dot, right? And then the 2s times this, you get y dot u of t. Okay? Yeah. And then based on this differential equation, it's just like a difference equation. Remember in the previous lecture, how do I get the discrete model from a difference equation? I pick the state, right? I pick the states. Okay? You pick a state variable here. So here's what we pick. This y is output. Suppose y represents position. Then y dot must represent is velocity, right? So let's pick x1 of t as y of t. And pick x2 of t as y dot of t. Is that okay? Yeah. That's very typical for a second order system. That's what you can do. Okay? Yeah. So in other words, my first state variable represent is physically represent what? First state variable. This guy. The position, right? And my second state variable represent is velocity. So this is key here, because why I'm trying to do this manually, not by using MATLAB or any other tools. Okay, I'll show you how to use the tools. The reason is you do manually, you have control as to what are the state that you choose. Okay, and you know exactly this position, this is velocity. Okay, then what is x1 dot then? It's y dot, right? And it's basically x2 of t. And what is x2 dot then? It's y double dot. Okay, it's y double dot. And the y double dot equal to what? Move this chunk to the other side. Okay, it's negative 2 y dots, which is x2 dot. Right? Yeah. So these two equations together, you have the state space model now for the continuous system, right? Which means you get x1 dot, x2 dot equal matrix times x1 of t, x2 of t times u of t. Okay, so single input, single output here. Okay, yeah. So what is the matrix that is here? First equation, 0 and 1. Second equation, 0 and negative 2. 0, 1. That's the continuous state space model. Okay. In other words, this is my F, this is the G, right? According to my previous notation. Okay. Yeah. So this basically one example that answer your question, Blake. See this F right here. This is not a non-singular matrix, right? Yeah. And what about the output equation? Output is C times X, and output is just this Y is the same as X1, so okay, and there's no D, so that's it. There. So now we're basically trying to obtain now is to discretize this guy, right, with what we learned today. So my discretization is to get x of k plus 1 equal to a x of k plus b u of k. And a at here, as we learned, a equal to e to the power of f times capital T, and b equal to this. Okay? Yeah. How do I get e to the power f of t? As we said, what first we do is we try to obtain e to the power of f small t, right? And then we'll replace the small t with a capital T. Okay? And e to the power of a small t, the formula we said it's the inverse Laplace of the inverse of this. Okay. So capital F is already have here. Then what about the inside here? So let's see. Inverse of what is Si minus F? Right? F is 0, 1, 0, negative 2. So what do we get? It's a matrix. So S times identity matrix minus this chunk here, right? Minus this chunk. So what should we have? It's S at here, negative 1 here, 0 here, S plus 2. Then inverse, right? Yeah. This is a 2 by 2 matrix. The inverse of 2 by 2 matrix, you should know that by heart, which is, what is the inverse 2 by 2 matrix? It's 1 over AD minus BC, and then D A at here, negative B, negative C, like that. Huh? Yeah. So if I use that here, what do we get? AD minus BC. So this times this minus this times this. So that just actually is this, right? And then inside here, you shift this S plus 2 over here, change this position. The negative 1 becomes 1 and 0, right? Yeah. And if you're not too sure, try to use this, multiply by the original one here, see if you can get back to this identity matrix, right? Yeah. Okay, so multiply this term into the matrix here, right? Into the matrix. And for the first term, you get S plus 2 cancelled. For this one here, nothing changed, so just like that. For this term, S plus 2. Okay, right? Yeah. So ultimately, now it boils down to the inverse Laplace of this matrix. Inverse Laplace of each one of the elements, right? Each one of the elements. Okay. So if you look at your table, what's the inverse Laplace of 1 over S? I actually don't need to look at the table. You should have learned this quite so many times now. 1, well, in other words, is actually unit step input, right? U of t. And what is the inverse Laplace of this guy here? Yeah. What about this guy? Well, you can hard to tell, right? But you can always do a what? Partial fraction expansion. So the question is, would that be 1 and 1 here, right? It's hard to tell, I guess. It's probably not. It should be, actually it should be 1/2 minus 1/2. Okay? Yeah. Then the inverse of this is 1/2 u of t. Yeah, you just have to be careful here, is because we typically u of t is the input, but now this is actually a step function. Okay, this is not the input function. Okay, the step function here. 1/2. Okay, that's it. That's the that is the e to the power of ft, right? E to the power of ft. And the last step, replace the small t with capital T. We get the A matrix. Okay, get the A matrix. So, I mean, u of t, essentially it's like you're sampling it. U of t, it doesn't matter where you sample, it's always what? 1, right? It's always 1. And here's always 1/2. And then you replace that, okay, with capital T. Okay, there we go. That's your A matrix, right? A matrix. And capital T is 1 in this particular case. Then you get the number here, right? Yeah. By sub the T equal to 1. Is that good? Yeah? So every step is clear, right? Now time to deal with the B. Okay. The B, we still start with this E of ft here. We replace the small t with lambda, right? With lambda. Okay. So let's look at the B here. So B equal to integral equal to this. Okay, so I'm integrating basically 0 to t. This matrix out of here, right? This matrix. Replace the t with lambda. Okay. So what do we got? U of lambda minus half of t u of lambda minus 1/2 e to negative 2 lambda 0 e negative 2 lambda times G matrix. What is the G matrix again? 0, 1, right? 0, 1. And then d lambda. Okay, d lambda. Okay. So how do we do with the u of lambda? This is the integral between u and the t, 0 and the capital T. So it's the integral with greater than 0, right? At greater than 0, this u of lambda is actually always 1, right? It's always 1. Okay. Yeah. And the other thing is, you can also do this first. Use this matrix times this vector first. You actually get rid of a lot of terms, right? You don't need to basically integrate every one of them. Okay. So then you actually just okay. You can do basically integral 0 to t. When you use times this, what do we end up with? Just a vector now. So 1/2 minus 1/2 e negative 2 lambda, and then e negative 2 lambda, and d lambda. Okay? Yeah. So integration of the two elements that are here, and that's should be pretty straightforward, right? Yeah. What is the integral of this guy here, first of all? Second element here, this is what? Negative 1/2 0 to t, right? Okay. And top one here you can try too. Okay. but overall you will end up with this. Okay, that's the B matrix. And once you substitute this capital T equal to 1, you basically got two numbers sitting here. Okay, got two numbers. Was that good?
How do you get
G
G matrix?
matrix. G?
Yeah.
Oh, that's our continuous state space model here.
Oh.
Yeah. Okay. Yeah. This is probably by far the most computations that are involved, right? Yeah. If we don't count one assignment question. Yeah. Okay. All right. So, and I want you to verify this, A and B values. Okay. See if you could get what you get, what I have in the lecture notes. Okay, lecture notes. So the other way, if you're using MATLAB to get this AB matrix, is pretty straightforward. First, you define your F matrix. Then you define your G matrix. Okay, so define the F and the G. Then the A, B matrix is C to D again. Okay, putting this F and the G, and putting the sampling time, you'll get this F and the G. You'll get A and B. Okay, it's pretty simple. All right, yeah. The default is zero order hold, right? Default is zero order hold. You can always put in that Lecture08 shader here, but if you don't, the default is zero order hold. Okay. So the other way of getting a discrete state model, you can check my lecture notes, MATLAB code. Okay. In that particular case, okay, I didn't define. You can take a look at that. I didn't define like the state variable like this, because the F and the G are created based on this set of state variables, right? If you purely rely on the MATLAB function and without considerations of what state variables you wanted to pick, you actually can do that too. Okay, but you will get a totally different state space model, basically, which means the state variables from that model is different. It's not a position and velocity. Okay, yeah. Not that it's wrong. Okay, it's just when you have a better control of that, we say I want to control that state variable, right? I want to control the other state variables. It'll bring some complex, complications. I think I'm going to stop here. Any questions? Just a little bit left here now. Just like a lot of writings. Okay, any questions? All good? Okay, thank you.